let's take a look at one more example here together with some slightly more complicated functions. So far we've really only been looking at some very basic, simple kind of polynomial functions. And it's important for us to recognize that the reason that I include a lot of those functions in the notes here is so that we can kind of focus more on the new calculus ideas and not be so concerned with how exactly we're supposed to work with more complicated functions at the start. But of course, this is why the worksheets, as you probably have noticed, contain questions that tend to be a little bit more involved than some of the stuff that we do in the notes. Because once I understand the calculus concepts, I'm ready to kind of increase the difficulty of what I'm working with. So let's try to do that here together. On what intervals would this function be increasing, decreasing, and can I state all the local extrema for the graph? All right, well again, we know where we have to start. We need to start by just trying to calculate our derivative. So notice that our derivative here, though, is going to have to be found by using a product rule because we have a multiplication of two items here. So I'm going to have 2x times the natural log of x, and then plus x squared times 1 over x. If I simplify this down, this is 2x natural log of x plus just a single x. And of course, I could take this one step further by recognizing that I can factor an x out of what I have here, and I get 2 natural log of x plus 1. So this is kind of a fully factored form of my derivative, and now of course I'm interested in finding my critical values. So I'm going to state f prime of x is equal to 0 whenever x times 2 natural log of x plus 1 is equal to 0. Of course, this is going to lead me to either x is equal to 0 or 2 times the natural log of x plus 1 would need to be equal to 0. So x equals 0 is a very easy critical point to see here, but I have to kind of solve for this other one. Notice that this would require that natural log of x would be equal to a negative 1/2. And if I take both sides and make them powers of e, I would see that I get x is equal to e to the negative 1/2. So I have two critical points here. Notice that one of these is actually kind of a not so fun value. Now if I was to go to a calculator, I could figure out roughly what this value is. And so I'll do that here. I'm going to go ahead and I'm going to type in e to the negative 0.5, and I can see that that's a value of around 0.6. So I can go here and just note to myself, this is roughly about 0.6. Okay, I can also find now when my derivative is going to be undefined. So I can say f prime of x is undefined. Well, let's see. What would be the values where this would be undefined? Well, there are some values that I'm not allowed to plug into the natural log. And those would be any value that's a 0 or negative. So I can go ahead and say that my derivative is undefined for x values that are less than or equal to 0. So at first glance, it looks like I have a lot of critical points, but I should note that actually all of these values are not critical points because they're not even in the domain of the original function. I couldn't even have plugged these numbers into the original function. So these here are not in the domain of f of x. And remember, that's one of the criteria to be a critical point, is you actually have to be a number that corresponds to a point on the original graph, although you can't have a critical point. So it seems like the only ones that I need to worry about here are actually going to be critical values of x is a 0 and x is an e to the negative 1/2. Ooh, wait a minute though. Can x be equal to 0? Well, we actually said down here that that's also not okay. So this is going to get removed as well. It's not able to be plugged into my original function. So actually then the only critical value I have is e to the negative 1/2. So I can go ahead and I can plug in e to the negative 1/2 right here. And I can note that when I did this, my derivative spat out the value of 0. And now I'm going to test some values on either side. Notice I could test a simple value like 1, which would definitely be larger than my value of e to the negative 1/2. And notice if I plugged in the value of 1, x would be positive. Natural log of 1 is 0, and so this inside here is positive. And so I would get that this part over here is ultimately just positive. Now if I plugged in something else, like maybe say I plugged in a value of, I don't know, say a something smaller than 0.6. How about I plugged in something like a 1/2? Well, then this piece here would be positive, and I'd have to double check here. 2 times the natural log of a half plus 1. Well, let's see. 2 times the natural log of a half plus 1, that's going to come out as a negative amount. And so I could see then that if I plug in a value like a 1/2, I'm going to get a result here that's negative. So of course I can see then that my graph appears to go down, 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 levels out to 0, then starts going back up. And so at this point here, I have a minimum. So I can summarize everything by saying f of x has, or maybe I should say is, increasing on the interval from e to the negative 1/2 up to infinity. It is decreasing on the interval from negative infinity to e to the negative 1/2. And I can see here that I want the local extrema of the graph, and it looks like I only have one. I have a local, let me rewrite that. I have a local minimum value, a local min of f of e to the negative 1/2. Remember again, local mins, local maxes, they are y values. E to the negative 1/2 is just where it occurs. So I'm actually going to have to go back to my original function and plug this in. Well, notice that's actually not too hard. Notice if I was to take e to the negative 1/2 and square it, that's just going to get me e to the negative 1. And if I did the natural log of e to the negative 1/2, I'm just going to get negative 1/2. And so I ultimately end up with a value here of negative 1 over 2e. This is my lowest value on the graph. There are no local maximums. So of course this problem was a little bit more involved than some of the ones that we're working with. I had to consider the domain of my original function. I had some messier numbers to work with, but hopefully you can see that the calculus concepts are all still the same. And that's really the main driving point here.